Here, for example, is a song about exponential growth. Are you ready for this? Here's a song that's meant to warn you or enlighten you or both. It's a little complicated, but you really need to know. There's a dangerous phenomenon. I swear to you an oath that there's trouble in this world from all the exponential growth. You can sing that, actually. Exponential growth. Oh, exponential growth. Yes, there's trouble in this world from all the exponential growth. Oh, exponential growth. Look out for exponential growth. Yes, it's creeping up behind you. Yes, it's exponential growth.
All right, well, welcome back, Algebra 1 students. So we are talking about exponential growth and decay in this lesson. So not just growth, but we're also going to be looking at decay. And so as that kind of song was just getting us introduced to just the idea of exponential growth, it does kind of creep up upon us. It's something that goes up very quickly and can rise very fast. We actually been already looking at some of those graphs from last time and seeing that it's like that Superman ride at the Magic Mountain, or it's like a plane that, or a rocket ship that just takes off. It kind of goes along the ground kind of slowly at first, but then all of a sudden it just takes off to the sky. And so it just rises up really fast. And the decay just does the opposite. It comes down really fast and then it kind of levels off on the ground, kind of just never goes away. And we need to remember that there's always a ground somewhere. There's always an asymptote, we called it. That's that line that you just don't cross. And so we need to remember that as well as we kind of continue on with looking at even just this exponential growth. We're not going to look at the graphs this time. We're going to be more focusing on the exponential growth and decay models in this lesson. So that's what we're looking for. We're going to be identifying exponential growth and decay from the actual model function. So before we get into that, let's go ahead and look at our cartoon for the day. So here's a Far Side cartoon. It says, donning his new canine decoder, Professor Schwartzman becomes the first human being on Earth to hear what barking dogs are actually saying. And all of them are just saying, hey, 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 in the background. Not too much. He was not enlightened too much there. All right, well, let's go on to looking at our core concept and some vocabulary. Here on page 314, right there in your vocabulary, it says exponential growth. Here's what you should write down for exponential growth, is that it occurs when a quantity increases by the same factor over equal intervals of time. So, one, I highlighted increases. It is increasing. Increasing obviously gives the idea that it's going up. Okay, it's going to keep climbing and it's getting higher, it's going up, it's increasing. And that quantity does that by the same factor. Now the factor is always something you would multiply by. So we're always multiplying by the same number every time. And when we were looking at linear functions, we were always either adding or subtracting a number, the same number every time. Well, in exponential functions, at least on the y, for the y, the y in the ordered pair, that y coordinate, we're going to be multiplying by the same number every time. And it says it's over an equal interval of time. And so it needs to be over that equal interval of time. And typically it is in terms of time, you start with the very, year 0, you start at 0, and then you go on to, okay, after 1 year, after 2 years, after 3 years, after 4 years, and it's that same just 1 year after the other year after the other year. Typically, that's what we are looking at with time. Most of the time it is in terms of years, but sometimes it does, do it in terms of maybe hours or something like that. Now, the core concept right there on also page 314 shows you the exponential growth function. Now, this is the model that we're going to be looking at. Here's the model right here, and it explains what every little thing here means. And so we see this model. Now, what we need to realize is it's the growth model. And so when we're looking at some of these, we got our y first is just the final amount. It's what you would have at the end of whatever time frame you're looking at. The initial amount is the a in front of this parenthesis. So whatever number is here is the starting amount. Now that's what you want to realize here. Initial is the same thing as saying starting. So that is the starting amount, what you start with or what you begin with. And then the r inside here is the rate of the growth. and it's always going to be in decimal form, so it will probably show it to you in percent form, like a 2% or a 5% growth rate. You got to put that back into decimal form if you're going to put it into the formula. This is kind of like a formula model. So when you put it into the formula, you have to put it in as a decimal. T stands for the time. That's usually, like I said, in years. So it could be like 1 year, 2 years, 3 years, whatever. That's your T. The parenthesis here, which is actually the base for your variable T, is called the growth factor. So that would be our growth factor. And that has to be, and if it's growth, this has to be more than 1. That's why it's 1 plus the rate. That will definitely be more than 1. All right, let's take a look at example here. You don't need to write this down, just watch what we're doing. It says the inaugural attendance. Inaugural means the very beginning, the very first one. The inaugural attendance of an annual music festival is 150,000. The attendance Y increases by 8% each year. So there's that percent. In letter A, it says write an exponential growth function that represents the attendance after T years. So we're going to plug it into the model that we were just looking at in our core concept. So we start off by saying the initial amount is the 150,000. Your rate of growth is the 8%, but when you put it into the actual function, you got to put it in as 0.08. So what percentage is always, you move the decimal back 2 places. Right now it's like 8.0, so you move it back 2 places. So there's going to be a 0 in front of it, 0.08. So now here's the model that we were looking at. We're going to put in our A and our R right now. So A is the 150,000, the R is the 0.08, and now we're just going to add the 1 plus this 0.08 to get 1.08. And that's all they needed you to do. That is doing A, writing the exponential growth function. So there it is. Letter B says how many people will attend the festival in the 5th year. So it says round your answer near 1,000. So if the inaugural one would be, and the inaugural is the very beginning, that's the starting amount, that would be actually year 0. Because if you put in 0 for T right here, that's going to give you 150,000. You're going to have 1.08 to the 0 power. Anything to the 0 power is always 1, and so it'd be like 1 times this 150,000. That is the beginning or starting attendance. So after the 5th year, the 5th time they would have this, that's actually going to be T equals 4. So 4 represents the 5th year because T equals 0 represents the 1st year. And so if we plug in 4 for T right here, we put a 4 in, then we can then use our calculator to figure this out. We do 1.08 to the 4th power times 150,000. That's going to give us our answer right here. So that's what we would do on the calculator. Let me show you what we would maybe look at if I pull up the calculator on my computer here. I'll show you how they would have got that. I would have put in the 1.08 first. Now some calculators are different than others. This one requires me to put the base in first. Here's my x to the y power. I'm going to click on that. That gives me my little arrow up here showing me the next number is an exponent. And so 4 is the exponent. So there it is. That was what the 1.08 to the 4th power would be. Then I just multiply by my 150,000 and then hit equals. And there's the number that they got down here. They rounded it to the nearest whole number, looks like right there. Nearest 1,000. Actually, the nearest 1,000 is what they rounded it to. All right. Let's take a look at our problems now. So extra practice on the next page. So I'm going to have you try this number 1 problem as I just showed you that one. Let's try this one. So I'm going to give you a minute to try this. Go ahead and pause the video. It says in 2005 there were 100 rabbits in Polygon Park. The population increased by 11% each year. So you're going to do A, write that exponential growth function that represents the population T years after 2005. And then also, so do this one first. Do A first. So pause the video and let's get A correct. So do A first and then we'll look at B. So go ahead and pause the video and see if you can figure out what the right functions should be. All right, so you should have an answer for A. So first of all, what I put here is the letter A in the function. The initial amount's 100. There's 100 rabbits at the beginning. The rate is 11%, but we need to put that in as a decimal. Remember, it's like 11.0. Move it back 2 places, so 0.11. So if we put this in for A and our R, so there's where it would start. There's your A number, there's your R number, and as you put these two together, then it would be this. So y equals 100, and then our base is 1.11 to the t power. Then it says, what will the population be in 2025? So that's 20 years after that. So 20 years after that. So t is 20 years. So you're going to put 20 in for your t. So you can see we can do that right there. So y equals the 100, your base 1.11 to the 20th power. Okay, so I want you to see if you can use the calculator and get this correct. So it says round your answer to the nearest whole number. So what would the population, how many rabbits would we have after 20 years if it was going to grow with this growth factor, and if we started with 100 rabbits to begin with? So go ahead and pause the video, see if you can do it on the calculator correctly and get your answer right, and then I'll just show it to you once you play the video again. Okay, so hopefully you've got an answer on your calculator. Hopefully it will be the same answer that I have here. So what we want to do, if I do 1.11 to the 20th power, that would give me a decimal of about 8.06, and then just 100 times 8.06 is going to give me 806. So there should be around 806 rabbits after the 20 years. So again, I'll show you on the calculator how I would have got that. So I would have put in my 1.11 first, 1.11, and I'm going to raise it with my x to the y power. Now some calculators, the button is a little different. On some of them it actually just has this little arrow button. Actually the button actually shows the arrow. And then 20 is my exponent, and equals, so there's that decimal that I put in here, and then just if I say times 100, and there's 806, again rounding to the nearest whole number, would just be 806. Okay, back to 314. Now let's take a look at the exponential decay. So it actually is very much the same thing as growth. It's just going the opposite direction. So it's the same thing here, just decreases instead of increases. So what you could write down for exponential decay is that it occurs when a quantity decreases, again highlight the decreases part, by the same factor over equal intervals of time. So again, it's still going to be multiplying this time, but this time it's going to decrease, so that what you're going to be multiplying by is going to have to be less than 1 in order for it to be able to decrease. When we're doing growth, you have to multiply by something that's more than 1. That's why we always had 1 plus the rate in the growth factor. And so when you look at your core concept here on that same, actually I think you're on the next page there for this one, but look at the decay, exponential decay function. The only difference in the function is instead of a plus r, it's now a minus r. You're subtracting the rate. That way, your decay factor here will actually be a number that is really between 0 and 1. Make sure you understand that right here, that the r has to be between 0 and 1, which tells you that your base, your decay factor, whatever this is never going to be negative. You cannot have that being a negative number. It's going to be either more than 1, and it's going to grow, or it's going to be between 0 and 1, less than 1, but still not negative, and it's going to decay that way. It still has your final amount being y, your starting amount being a, and your r is your rate still, it's just a rate of decay. T is still the time, so the only difference there in this is just a subtraction though, instead of addition. Alright, let's go on to looking at this next one. You're just going to go ahead and watch this. You don't need to write this down. We're just trying to look at a table of values here, given your ordered pairs, and see, does it represent growth, decay, or does it represent neither one? So on this one, letter A, we can see that on the X, we are going up by the same amount. That's like the time. So year 0, year 1, year 2, year 3. So every year, one year after another, going up by ones. What is the Y doing? Well, the Y is going down. Okay, so this would be decay if it's going to go down, but it's going down by the same amount by multiplying by 1/3. You could also divide by 3. You could think of, okay, I'm going to divide by 3 and get 90, divide by 3 I'm going to get 30, divide by 3 I'm going to get 10. Dividing by 3 is the same thing as multiplying by 1/3. We always want to see that factor, that decay factor or the growth factor, by what we're multiplying by. So it's multiplying by 1/3, which is between 0 and 1. So this is definitely representing exponential decay. On B, we can see our x here, 1, 2, 3. It's going up by 1 every time again. And 5, 10, 20, 40, you're multiplying by 2 every time. So this one has a factor of 2, a growth factor, because it's more than 1. 2 is more than 1, so it is going to grow. All right, so hopefully you understand this. Now, if it's not doing either one of those, if it's not being multiplying by the same number every time, either less than 1 or more than 1, then it's going to do neither. It's not going to be a growth, it's not going to be an exponential function. All right, so right there back on your extra practice, 2 through 4 gives you 4 of these table of values. What we're looking to see is it representing exponential growth, decay, or is it neither? So one of these, I'll tell you, is neither. One of them actually represents linear instead of exponential. So go ahead and pause the video and go through 2, 3, 4, and 5 and see if you can figure out which one is exponential growth, which one is exponential decay, and which one is actually going to be the linear function out of those 4. So pause the video and then play it to check your answers. All right, so let's check our answers now for 2 through 5 and see if you get these right. So on number 2, you can see for the x, we are going up by 1 here. So each time you are increasing by 1 every single time. I'm not going to do all 3 of them. If you want to do it, you can. But we're going up by just ones. On the y, what are we doing? 20 to 30, 30 to 45. So we are going up here. And you can say, well, am I adding? I can add 10 here. Well, this would be adding 15, so it's not going up by the same number with adding. So we are going to be multiplying this one. And this one is actually going to be multiplying by 1.5. Now, this might have been a little bit challenging because it's not just a whole number. It's like 3 over 2. If you multiply 20 by 3 over 2, like 20 cancels out here, 20 goes into, or 2 goes into 20 10 times, so 10 times 3 would give you 30. And if you did it again, you do the same thing, 15 times 3 would be 45. You cross cancel with 20 and the 2. So that's going to be doing this. You're multiplying, we are multiplying by 3 over 2. So this is definitely exponential growth. On this one. Number 3, we can see we are going to go up here by 1 again. What are we doing on this one? We are going down this time. So we are dividing. If I divide it by 4, I'm going to get to 40. If I divide by 4, I'm going to get to 10. So if we're dividing, what are we multiplying by? 1/4. So that's going to be between 0 and 1. So that is definitely exponential decay. On number 4, we are going up by 1 every time again here. On y, however, let's see, we are going down. 32 to 22, 22 to 12, 12 to 2. We are going down, but by 10. We are subtracting 10 every time. And so since that is just going down by the same number every time in a subtraction, this actually would be a linear function. This is the one that would have been linear. So it's neither exponential growth or decay. Number 5, we are going to go up by 1 here. 4 to 10, 10 to 25. Again, this one's a little more challenging. What would we multiply 4 by to get to 10? Because we're obviously not adding. We're adding 6 here, then you're adding 15, so that's not it. So what would we multiply by from get 4 to 10? So let's just go ahead and try multiplying by 5 over 2. So 5 over 2. Again, if I cross cancel here, 2 goes into 4 twice, and then 2 times 5 would give us 10. And I can do the same thing here. 2 goes into 10 5 times. 5 times 5 is 25. So that would be it. We are going to be multiplying by 5 over 2 every time. So that is growth, because 5 over 2 is more than 1, because it's an improper fraction. So we got growth on number 5 as well. So hopefully you're able to do those. If not, then that's fine. Hopefully you're able to see and understand now what we were doing. Especially I know 2 and 5 were a little challenging because of the fractions that we got here. This was either 1.5 or 1.5. This was like 2.5 or 2.5. All right, let's move on to our next part, which is our joke of the day. So what lies at the bottom of the ocean and worries? So it's at the bottom of the ocean and it worries. Well, that's a nervous wreck. A nervous wreck. Because it worries, it's nervous. And a ship that's at the bottom of the ocean, you call it like a shipwreck. So it's a nervous wreck. All right, moving on to our next part. We're going to be now looking at just the function and identifying if it's exponential growth or decay, and then identify also what the rate is. Again, you don't have to write these down, just go and watch. So we're looking at letter A here. So 1.07, that right there is more than 1, and you have it just to the t power here. So you can, when it's just to the t power, you can look at your base and see if it's more than 1, which it is, so it's going to be exponential growth. It's like the 1 plus the r, so it is growth, exponential growth. And your growth rate basically is how far away is this from 1? Well, it's like 0.7 away from 1. So your R would be 0.07, which if you think of it, you know, if 1 is like $1 and this is like $1.07 here, it's like you're 7 cents away from $1. You're 7 cents over $1. So that's 7 cents or 7%. Okay, so 0.07, move the decimal back 2 places, your growth rate is 7%. If we look at B right here, B, 0.98 is less than 1. Again, it's just to the t power, so we can look at our base. It's less than 1, so it is exponential decay. But how far away is this from 1? Again, think of it in terms of money, like $1 is 1. This is like 98 cents. So we're 2 cents away. So rate here would be 2 cents, 0.02, which 2 cents would be 2%. So it's actually a rate of 2%, a rate of decay of 2%. Okay, so that's where you want to kind of think of it. Where are you on 1? If it's growth, it's a little bit more than 1. If it's decay, it's a little less than 1. And you got to see, okay, how far away are you from 1? That's always your rate. And you got to turn that rate from a decimal back into a percent when you want to describe it. All right, let's go ahead and look at 6 through 8. So same thing, I'm going to have you do these on your own, 6 through 8. So go ahead and try these to figure out if it's growth or decay, and then also identify the percent rate of change. What should the percentage be of the rate of growth or the rate of decay? So go ahead and do 6, 7, and 8, and then go ahead and play the video and check your answers. Okay, so let's look at number 6. So if we had an answer for 6 here, we could see that it's less than 1 right here. 0.95 is the exponential decay because it's less than 1. And again, we're looking at this will be our percent rate of change is down here. Our percent rate of change on this one is going to end up being, oops, just move this down like that. So 1 minus R is equal to 0.95. So basically, what do we need R to be? We're at 5 cents away. So 0.05 is what we need R to be. And so we move that back 2 places. It's 5%. Our rate, or R, is 5%. Number 7. Here's your base is 1.08 and it's to a t power. So we can just look at the base. So if this was not just a t power, we couldn't just look at the base. But when it's just a t power, or just the variable by itself, you can look at the base for recognizing exponential growth or decay. And you can see it's growth on this one. We're more than 1. And we're 8 cents more than like $1, like $1.08. So on this one, that should be 1 plus the 0.08. That 0.08 is your R. And so 8 cents would be the same thing as 8%. Move the decimal back 2 places for 8%. And this one's got a fraction, but it is less than 1. 3/4 is less than 1, so it's exponential decay. And we want to think about this maybe as a decimal. What would 3/4 be as a decimal? You could just do 3 divided by 4 to see it's 0.75. So what should the rate be if we're at 0.75? How far away are we from 1? Well, we're like 25 cents. It's like 75 cents, so we're 25 cents away. So that 25.25, we change it back to a percent for 25%. So there's our rate. All right, hopefully you did well on those and that you understand. Let's go on I'll give you a couple more of these to try here in just a moment. Okay, again, you're just going to watch these ones. Just look at these. It's very similar to the last ones, but now notice that you don't just have a t power. You have t over 4 power, and this one you have a t minus 3 power. So we can't just look at the base now. We have to deal with the power first to get this to be just a t power by itself, so we can look at the base to determine whether it represents exponential growth or exponential decay. So what we need to realize is this is being divided by 4 here, which is the same thing as multiplying by a 1/4. And so for this one, it's like t over 4. We can say we can raise the 0.96 to a 1/4 power, and then whatever that is, we can see if it's growth or decay. So how would we do that? Well, we'd use a calculator. Okay, so you use your calculator here. Now, 1/4 is 0.25. If you want to just go and check that, 1 divided by 4, it's 0.25. So that's the exponent you would need to raise 0.962. So we can use that decimal as a 1/4, or we could try doing 1/4 as a fraction. It's a little bit harder though, because you'd have to use parentheses for that. So let's go ahead and try 0.96 first. And I'm going to use my exponent button. And my exponent is the 1/4, but I'm going to put in 0.25 to represent that 1/4, equals 0.989, so that's what we should see over here, 0.99. Now we can see, okay, that's just a little bit less than 1, so we're talking about decay for that one. On letter B, it's got t minus 3. So this t minus 3 is like you can subtract exponents. You can make this into a fraction. So you could do it this way. You could do 1.1 to the t power over 1.1 to the 3rd power. And so now you can just see, well, 1.1 to the t power, that is, you can just look at that there. On that one, it's more than 1, so it will be growth on this one, because this eventually will become 0.75 or approximately that, which will go in front here. So now you can just look at your 1.1, which is exponential growth. Okay, so on your notes, on page 186, right at the top, you're going to see underneath the core concept of exponential decay, I want you to put these, the 4 through 7 here. You can say 4a, 5a, 6a, 7a. You can label it like that if you want to. But go ahead and try 4 and 5. 4 and 5 are just like we did before on the extra practice. It just is to the t power. And you want to also identify the percent rate of change on that one. But 6 and 7 are like I was just showing you. Here's a 10t power, so you got to deal with that first. Here's a t plus 2 power. So deal with that first to identify if it's exponential growth or decay. So go ahead and pause the video and do these right here on the top of 186, right in that notes section underneath exponential decay model. Okay, you should have paused the video, and let's go ahead and check to see if you were able to do these right. So this number 4 problem, it should have been exponential decay because you're less than 1, and if this is 92 cents, we're 8 cents away. It's an 8%. So you should have exponential decay. 8% is your percent rate of change. This one here is more than 1, 1.2. So you have exponential growth. How much more than 1? Well, it doesn't really show the extra 0. Like if you make this into money, we're actually at $1.20. So it's like 20 cents or 20%. So the 0.2, you move the decimal back 2 places, you're at 20% growth. For number 6, you'd have to deal with this first here. So let me actually do that kind of on the side. Let's see if I can get this. Show you this one here on the side. So what we do here on this one is I'll just start with a 3, and then the 1.02, and I'm going to raise this part here to the 10th power. And then maybe put this in a bracket right here around that, and then I'll raise it to the t power there. So I need to raise the 1.02 to the 10th power on the calculator. So if I grab my calculator again, and I do 1.02, and I'm raising it to the 10th power, that would give me this 1.22 number approximately there. So now I'm going to see it's going to be 1.22 to the t power. Now I can definitely see that that is exponential growth. So that would be the exponential growth there. And there you can see what I wrote down. So you should write that down. That's what you should have to recognize exponential growth. It says rewrite the function to determine whether it represents exponential growth. So you're rewriting it as this, just like I wrote it here, and it's exponential growth. Now for this one, number 7, so again this one was 6 here, number 7, we would start with the 0.95. So this is the plus. The plus means you're going to add exponents, so it's like you got a 0.95 over here. Am I there? No. Where am I at? Pen. Do I have my pen? Yeah, I guess I do have my pen. Okay, 0.95. Just has the hand. That was throwing me off there. To the t power times 0.95 to the second power. So you want to do this part first, 0.95 to the second power on your calculator. So 0.95, raise it to the second power, or you could just do squared because it's just a 2. I do have a squared button, so I can do that. So it's basically 0.90. I'm just going to do 0.90 because I think that's what they're going to say. So it's going to be 0.90 in front of this 0.95 to the t power. And so now you can see 0.95 is definitely less than 1. So this was exponential growth, but this would be rewriting it the way they want it written. 0.9 or 0.90. I did 0.90, they did 0.9, that's the same thing. Exponential decay because 0.95 is less than 1. Alright, let's move on to our next part. Hopefully you're understanding if we're looking at the base number, and the base number can only be looked at as long as your exponent here is just the variable by itself. If it's not by itself, then you have to rewrite it first so you can get it by itself, and then you can look at the base number to determine if it's more than 1 for exponential growth or if it's less than 1 between 0 and 1 for exponential decay. Alright, so our next core concept right there at the bottom of 186 is this compound interest. Compound interest uses the same kind of model as this exponential growth model. We usually talk about compound interest when we're talking about money in the bank, and typically if you put your money into a bank account like a savings account, there sometimes is an interest rate, and you gain interest on this money, and it's compounded usually once a month. Typically it's once a month. So compound interest is the interest earned. Now you don't need to write this down in your vocabulary because you have it here. You can just highlight it in your core concept. It's the interest earned on the principal. The principal is the starting amount, like if you put in $100 to start with into the account. So that's the starting amount, and on previously earned interest. So it keeps compounding it over time. So as you earn interest, it compounds it on top of that number. And he earns it more interest. The next month, he compounds it on that number. The balance, which would be like your final amount, is the y. Okay, so it's still final amount, initial amount. You're just using different letters. They're saying P here for principal, but basically it's like your A here. Final amount, initial amount. You get your 1 plus the R. R is still going to be your rates. The interest rate, and it's going to go in decimal form. Your T is still going to be time in years, but the difference now is this N in here. The N is the number of times interest is compounded per year. So if it says annually, so there's a few things it might say for this. If it says annually, that equals 1, so N would equal 1 for that one. If it says semi-annually, N is going to equal 2. I'm going to give you the most common ones you would probably see. If it says quarterly, that means N is going to equal 4 quarters in a year, just like there's 4 quarters in a school year. And then also you might see monthly. Monthly is every month, so there's 12 months in a year. Those are the most common ones you will probably see. You might see, the last one that you may see could be, I don't have any space here, I'll put it over here, would be daily. If it says daily, that would be 365, because it's 365 days per year. But most of the time it's going to be one of these 4. Alright, let's take a look at an example of that. So it says you deposit $100 in a savings account that earns 6% annual interest compounded monthly. So write a function that represents the balance after T years. So your Initial amount's 100. Your rate has got to be as a decimal. So here's our compound interest formula. And your initial amount, starting amount's 100. Your rate has got to go in as a decimal, 0.06. 6%, like 6 cents, 0.06. It's not 0.6, because 0.6 would be 60 cents. And then the compounding monthly, so the monthly part, n is 12. So there's the 12 at the bottom here, and the 12 up in the exponent with the t. So that n goes in two places. So now you just want to simplify what's inside here to simplify this base. So you'd be doing 0.06 divided by 12, and then just 1 plus that number will be 1.005. And that's all they wanted you to do on that to get to this part right there. Let's go ahead and look at our last couple problems here. 9 and 10. Write a function that represents the balance after t years. I'll go ahead and do number 10 with you, and then you guys can do number 9 on your own. So let's take a look at 10 first. So $5,000 deposit that earns 7.2% annual interest compounded monthly. So this one says monthly, this one says quarterly. So monthly means n is 12, quarterly means n is 4, like I told you earlier. So first of all, let's figure out what each thing is here. So like your A or your principal, I put A here just because we were familiar with that, is 5,000. Your R, your rate, 7.2% as a decimal is 0.072. And N is monthly, so that's 12. So N is 12 on this one. So let's go ahead and plug it into our formula. So it's Y equals the principal or starting amount, 5,000. Then in parentheses, 1 plus the rate over N. So there's that decimal over the 12. And then your exponent is the 12, again, the N, times T. And then we just got to clean this up a little bit, do what's on the calculator. Let's pull up the calculator here. So if I do 0.072 divided by 12, there's my 0.006, so I'm going to get that. So 1 plus 0.006, and then I'm just going to put that 1 in front there. It's easy to do. Don't really need the calculator for that. 1.006. And it's, what, I messed up there. That should be 12t. Somehow I put 4t there. That should be a 12t on that one. Let's see if I can make that into 12. It should have been a 12t. There we go. I think I was going back up to what we did there on number 1 or number 9. Okay, so go ahead and pause the video. Do the same thing for 9. You just want to come up with the right function with t as the variable. Okay, so see if you can do the same thing for number 9. Then go ahead and play the video to check your answer. Okay, let's go ahead and check to see if you were right here. Your initial amount, your starting amount is 3,000. That's the A, or we could call it P for principal. The rate is 6%, so 0.06. And it's quarterly, so your 4 is your N. And so over here, you should have Y equals to 3,000. 1 plus the rate, 0.06 over 4, and then 4t. So on the calculator, what you should have got there was 0.06 divided by 4, that's 0.015, so that going right in here, 1 plus the 0.015, 4t is the exponent, and so it's just 3,000, parenthesis, 1.015 to the 4t. Okay, that's what you should have. So before we leave, I want to do one more thing, and that would be to see, okay, what would we actually have, because really the whole point of this is to calculate how much money would we have in the account if we didn't keep depositing anything else. We just left it there with the 3,000 or the 5,000, and we just let it earn the interest. How much money would we have, let's say, after 5 years? So you can add this into your notes right here. So after 5 years, what would we have? That means that t is equal to 5. And so I plug that in for our function here, y equals 3,000. And then we got the 1.015, and it's got 4 times 5, which is going to give you actually 20. So this is really going to be a 20 right here. I'll just put 20 now. 4 times 5. So let's pull up our calculator again. I'm going to put in my base. Actually, I'm just going to add 1 to this, and that'll give me my base. So there's our base, 1.015. I'm going to raise it to the 20th power. So x to the y button gives me that little arrow up. 20 is the exponent, and it equals that decimal. And then we're going to multiply by 3,000. So times 3,000 equals. So that would be $4,040.57. So let me write that down. 4,040. So 40 and 57 cents. So we'd have $4,440.57. So that's what we would have after 5 years. All right, so go ahead and pause the video. Do the same thing for number 10 using this model. So after 5 years, how much money would we have if this was the example? So pause the video and then play that to see if you can do that correctly on the calculator. So again, t equals 5. So if you got an answer now, you use your calculator. We're going to say y is equal to 5,000. And it's the 1.006. And 12 times 5, and I'll just do 12 times 5, which is 60 on this one. So 60 should be the exponent of 12 times 5. And then we plug up our calculator. And we're going to do our 1.006. And my exponent is going to be 60. So raising it to the 60th power equals. There's our decimal, and we times it by the 5,000, the starting amount, and it equals $7,158.94. So $71.58.94. $71.58.94. That's what you should have had, rounding it to the nearest cent. Okay, so hopefully you're able to do that, because that's really the point of all of this, finding compound interest, is to be able to calculate how much money you'd actually have after so many years. All right, so that concludes our lesson on exponential growth and decay, and I'll see you on the next one in 6.5. Have a great rest of your day.